In this video, let's identify some of the common network devices that we might find in today's network infrastructures. And of course, this is not a comprehensive listing, but these are some of the common devices you might run into. In this sample network topology, notice that we've got three locations. We've got the headquarters location, we've got the branch office 1 location, BR1, and we've got BR2. Let's take a look at some of the devices we see at these locations. And let's begin with the router. The icon for a router looks a lot like a hockey puck, you'll notice, but a router is one of the main infrastructure devices we have. A router does routing. In other words, it can take a look at a packet coming from a client, coming from a server, coming from some sort of a network device, and it can look at the addressing on that packet. Commonly, we use IP, Internet Protocol addressing. IP version 4 and IP version 6 are the variants of IP that we might be dealing with. More on that later in the course. But a router is going to take a look, usually at some sort of an IP address and say, well, if this packet, this piece of data, if it's destined for this IP address, let's figure out how we should forward it. Notice this router at HQ has three interfaces. We've got interfaces 1, 2, and 3. And if a packet is coming in, let's say from the internet, it might have a destination IP address that needs to go out of this port number 1, to get to the inside of the network. Well, the router is going to maintain a routing table, and it's going to hopefully know how to forward that traffic. And you'll see in this case that the router has a couple of WAN connections. Notice this connection that looks a bit like a lightning bolt? Well, this means that this is a wide area network connection. It's not connected locally within a building or around a campus. No, it's going to some distant location. And we've got a couple of WAN connections here. One is going through an IP WAN. We've got some sort of a dedicated connection out to Office BR1, but we're getting to Office BR2 in another way. We're going through the internet. And that's something we see a lot today because internet speeds are getting so fast, even in our homes. Why not take advantage of that and use a fairly low-cost internet connection to get to a remote office? One of the big challenges that we have, though, is security. The internet is an untrusted network. Lots of scary things might be going on in the internet. Do we really want to send our private, corporate, sensitive data over an untrusted network? Well, maybe. What we could do is create something called a VPN. A VPN is a virtual tunnel. We could have a VPN, a virtual private network tunnel that can securely connect these two locations. Traffic flowing over that tunnel can be encrypted. So if some bad person on the internet were to intercept that data, they wouldn't be able to read the data because it would be all scrambled up. And we could also get some assurance, thanks to this VPN tunnel, that the data had not been corrupted in transit. Those are a couple of different ways we might connect out to remote sites. Maybe over an IP WAN connection, maybe over the internet using a VPN connection. And also in this topology, we've got several different types of end user stations. We might have file servers that our end users connect to. They might be connecting from a PC. Maybe they're connecting from a laptop. Maybe their laptop or even smartphone could be connected wirelessly by connecting into a wireless access point. And that wireless access point, along with all of our other wired connections, they're connecting into a device called a switch. Now, this is an Ethernet switch. This is a device that operates at layer 2 of the OSI model, the data link layer. The switch is going to make forwarding decisions based on layer 2 information. You see these laptops, these PCs, these file servers, inside of them, they have something called a NIC. A network interface card, and burned in at the time of manufacture into that NIC is something called a MAC address, a media access control address. And the switch is going to start building a MAC address table inside of itself. And that table might look something like this. It might have a list of ports and a list of MAC addresses that live off of each of those ports. Let's say that port 1 goes to a MAC address of AAA. By the way, MAC addresses are 48-bit addresses, and I'm not going to take the time to write out a 48-bit address. I'm just going to abbreviate that. I'll say all A's, all B's, all C's. And let's say that a frame comes in, and it's destined, the destination MAC address is all B's. Well, the switch is going to see that, and it's going to say, all right, I need to send that out of port 2 because I know a destination address of all B's lives off of port 2. That's how a switch can make its forwarding decisions. It's going to learn what MAC addresses. Just by observing network traffic, it can learn what MAC addresses live off of what ports, and then when it gets a frame destined for a particular MAC address, it knows where to send it. And by the way, coming up in the LAN switching part of the course, we're going to have a couple of videos that define a couple of terms for us. Those terms are collision domain and broadcast domain. And we're going to see in those videos that every port on a switch is in its own collision domain. You see, back in the old days of Ethernet, a network segment had to be shared. Only one device could talk on a network segment at any one time. We used to have something called an Ethernet hub. And a hub was sometimes called a bit splitter because really that's what it does. It takes bits in on one port and just repeats them out all of the other ports. And with a hub, if I had maybe a couple of PCs attached to this hub, PC 1, PC 2, if I had a couple of PCs attached to this hub, only one of those PCs could be talking at any one time because they had to take turns talking on the wire. And if they both spoke at the same time, that would cause a collision. That would corrupt the data. And that's why we say that every port on a hub is in the same collision domain. But the great news is every port on a switch is in its own collision domain. And we'll have more on collision domains and broadcast domains in the LAN switching part of the course. But now let's get back to our discussion of some of these different infrastructure devices. We've talked about the routers and the switches and the end user stations that are going to be connecting into the switches, maybe using a direct wired connection, or maybe connecting in wirelessly. But let's talk about a few of these other devices. And in the upcoming videos in this module, we'll talk more about these devices. For example, we'll talk more about how a wireless access point operates, how it allows a laptop or a smartphone or other wireless devices, like a printer, to connect into the network wirelessly without having to have a wired connection. We've also got some security devices in this topology. We've got an IPS. That's an intrusion prevention system sensor. When traffic is coming in from the big, untrusted, scary internet, and it's flowing through the router before it comes into the inside network at the HQ site, all of those packets have to flow through this IPS. And this IPS is equipped with a massive signature database. Signatures of well-known attacks. If somebody is launching some sort of a well-known attack against our headquarters location, the IPS sensor hopefully is going to catch that. It's going to say, this pattern that I'm seeing in this string of bits looks very suspicious. It looks like this sort of attack. And that IPS sensor can drop that packet in line before it can ever go do damage to any of the inside devices. And notice that an IPS, an intrusion prevention system sensor, that sits in line with the traffic. That's a little different than what we see at the BR2 location, an IDS. That's an intrusion detection system sensor. Notice that it does not sit in line with the traffic. It's getting a copy of the traffic. So we've got a packet, let's say it's a bad, malicious packet coming in from this router. It's coming into the switch. Well, the switch can be trained to send a copy of that traffic down to the IDS, and the switch also sends it on its way. And if the IDS detects, much like the IPS would detect, that this is a bad packet, it matches the signature of a malicious attack, the IDS could instruct the router to start blocking packets coming from this source out on the internet. We don't trust them. Don't allow any more of their traffic in. And that can happen fairly quickly, but please realize that we might have had a few packets make it to the laptop. And sometimes just a few packets can do damage. And as a result, many people prefer to use an IPS as opposed to an IDS, because an IPS, it sits in line with the traffic, and in some cases, it can drop those malicious packets before they ever make it to their destination. Another security device is a firewall, and we can think of a firewall as a set of rules. Rules about what traffic can come into the network and what traffic can go out of the network, and we can have these different zones of security defined on a firewall. Let's say that on this firewall port, this is going out to the internet. So this might be considered our outside interface. And this port goes to the inside network. That might be considered the inside interface. And we might have a rule that said something like this. We might say, traffic from the inside can go to the outside, and any return traffic that needs to come back in from the outside based on a session that was started on the inside will allow that traffic as well. But we could have another rule that says traffic that started, traffic that was initiated from the internet, it's coming in initially on the outside port, let's block that traffic. And also notice that I've got a third interface here. This third interface points up to what we can call a DMZ, a demilitarized zone. This is where we do have devices that we might want accessible from the public internet. People on the internet might need to get to our public web server. They might need to get to our email server. Those devices are inside of our network, but we don't want to put them on the same subnet as the CEO's computer. We want to keep them in their own security zone. And we can create a DMZ zone and set up rules to say something like traffic from the internet can go to devices in the DMZ zone if we're using particular port numbers. Maybe we're using port 80 to go to the web server. Or maybe we're using specific email protocols to go to the email server. And here at the headquarters, notice that we have a router as one device, and the firewall is a physically separate device. But at BR2, maybe it's a smaller site without as many users. What we're doing here is using a firewall router. Many routers can be trained to be a firewall. In fact, some routers can also be trained to be an IPS sensor. If you've got a smaller remote office somewhere, you might consider doing that. Putting the firewall functionality, the IPS functionality, as well as the routing functionality all inside of your router. And we've talked about the router that's a layer 3 device that can route between subnets. We've talked about the switch that's a layer 2 device that's going to make forwarding decisions based on MAC addresses. But what is up with this guy, the multi-layer switch? Well, it's much like a router. Like a router, it can make forwarding decisions based on layer 3 information. We can have some ports acting as switch ports. We can have some ports acting as routed ports. It can give us a lot of flexibility. In this particular example, I'm using this multi-layer switch as a router. Each of these ports on the multi-layer switch, I'm pretending that they belong to their own subnet, their own separate address space. And to get from one subnet or one address space to another subnet, we've got a route, and that multi-layer switch can absolutely do routing. And finally, as just a couple of examples of network appliances, let's check out the cache engine and the NAS. What are these doing? Well, oftentimes when our users are going out to the internet and maybe they're pulling down all these graphic files, maybe video files from specific sites on the internet, in many instances, users are downloading the same information over and over. I used to work at a university and we had one of these cache engines, and what we noticed was at times between 20 and 30% of the traffic coming in from the internet was redundant. Somebody was downloading a picture from CNN.com or ESPN.com, and somebody had already downloaded that very same picture maybe earlier today or a couple of hours ago. And we're using bandwidth for all this redundant information. What we can do is have a cache engine that is going to cache. It's going to locally store on our network these images or maybe videos that are coming down from the internet. And if somebody else wants to go out to CNN.com as an example, and they're downloading the headlines, if the same graphics are used in that web page that were used maybe a couple of hours ago, instead of downloading those graphic images again, what we can do is retrieve those from storage. We can retrieve those from the cache engine, and that can ease the bandwidth burden on our internet connection. And finally, let's consider the NAS, the Network Attached Storage Device. The NAS oftentimes contains multiple hard drives, and frequently they're in a redundant configuration, so we can lose a hard drive without losing any information. And by having an appliance like this, a network attached storage appliance, that can be a more efficient way to make files available on a network as opposed to having something like a dedicated file server. Because oftentimes with a file server, you've got to have a physical server to house that on. You've got to install some sort of a network operating system on that file server. Then you put in the hard drives to the file server, and then you can share those hard drives with a network. Well, it can be more efficient with a NAS, network attached storage. It's an appliance whose sole purpose in life is to make these hard drives available to the network. And of course, it does have mechanisms for controlling who can read and or write to those hard drives. And this has been an overview of not all, but some of the common infrastructure devices we're going to see in modern networks.